Okay, this is 15.4, number 1. We're doing surface areas. We want to find the surface area of the sides of a right circular cone of height h and radius a. So let's draw it so that we can actually figure out what function to use for this. So here's its base, and then the height is h. So h, and then its radius is a. And we want to find just the area of the sides here. So the first thing I need to do is kind of express that surface area, or the surface itself, as a function. And it's pretty easy. We can just use the equation of a line that represents its edge. So z is actually going to be equal to some slope, and again, let's just say x for a moment. It won't really be x, plus b, whatever the y-intercept is. Well, we can fill these in. The slope is going to be negative h over a. Times x, and then plus, and the y-intercept is h. So if I rewrite this, this is h times 1 minus x over a. And of course, I don't just want this for x, because this isn't a triangle whose side represents that. This really is three-dimensional. That side swings all the way around. So I don't want just x to represent this distance. I want that distance to be the radius. And you'll notice it makes the same triangle no matter what the radius is. No matter how I draw the radius out, it still makes that triangle. So that's all I'm going to do is change x to r. So our z is equal to h times 1 minus the radius over a. And notice this automatically puts it in polar coordinates. So this is ready to be polar, which is awesome. If I want to integrate all of this, then my theta value is going to go from 0 to 2 pi. And finally, I want the radius to go from 0 to a. And then recall that I need the partials of this. So I need z with respect to r. And z with respect to r is just going to be negative h over a. And I need z with respect to theta, and that's going to be 0 because the surface area of a cone isn't a function of theta. So now I can build the integral. It's going to be the integral, we'll do the theta outside, 0 to 2 pi, times the integral from 0 to a. And then to build the function, it's the square root of the square of the partials plus 1. So that's going to be the square root of h squared over a squared plus 1, and then it's r dr d theta. Let me dress this up a little bit. You'll notice that whole thing is a constant, so I can just draw it outside before I even do any of the integrals. So that's what I'm going to do. So my first integral is really going to be the integral from 0 to a of r dr, and that's just going to be r squared over 2 between 0 and a. And that's just going to be a squared over 2. So now my constant outside is a squared over 2. And then I'll dress this up a little bit. This is going to be h squared plus a squared over a squared, and all that under the radical. And then that'll be the integral of, this is just going to be 0 to 2 pi of d theta. So all that's going to do is add 2 pi onto it. So this whole thing here now becomes a squared over 2 times 2 pi times the square root of h squared plus a squared, and that whole thing's under a because I took it out of the radical. The 2's cancel, the a's cancel. So it's a pi times the square root of h squared plus a squared. So that's what it says is the surface area by integration. And of course I can check this pretty easily. If you'll recall from your geometry that every single cone has the dimensions slant height L, and then the radius, which in our case is A, and of course its height. And if you'll recall, the surface area, excluding the bottom, was always 1/2 of the slant height times the circumference. So 1/2 of L times the circumference. And then let's see what that is. So it's 1/2. L would just be the hypotenuse of a right triangle, made up from h squared plus a squared. So it's the square root of h squared plus a squared. And then the circumference is 2 pi a. And the 1/2 cancels, and what do you know? It's pi a, the square root of h squared plus a squared. It's nice when things work.